Okay, y'all. So for today's lecture, I'm going to do a problem session for section 7.3 and 7.4. So I've had some students ask that I do more examples, that they feel like that would be helpful. And we're making a pretty good pace through all the topics. So I think it's good to just go over some more examples so you can see how to think through solving particular types of problems. So I went through 7.3 and 7.4 and chose 3 different problems from both sections to go over that I hope will be helpful to you. Okay. So in 7.3, we were learning about the binomial probability distribution and how to compute probabilities using the binomial probability formula. And so in this first problem, problem 3, you're asked to find the probability that a binomial random variable equals a certain value. And here they've told us that the value of the number of trials is 4, that we're interested in the probability of getting 3 successes, and the probability of success is 1/3. And occasionally my daughter will scream because she's staying home from school today, so I'm sorry if that is a distraction. Okay, so this particular computation we can do by hand, but I showed you last time how to use a calculator to do it. And so I just want to go over how to do it with the calculator because that's just quicker and easier and more realistic. So this is a binomial random variable. So to calculate the probability that x equals 3, we're going to use the binom PDF function. And remember that this takes in the inputs n, p, x. Okay, so n is 4, comma, p is 1/3. And then k is 3. So we can put this into the calculator to get to the binom PDF function. We turn on our calculator, hit second vars, and then scroll down till you get down to the binom PDF and CDF functions. We want the PDF. And then we're going to give it the inputs that we have up here. So 4, comma 1/3, comma 3. And it gives us the result. So the probability is 0.0987, and we'll just round to there, 77. So it's really that simple. Remember that if we were to do it by hand, then we would have to compute the binomial coefficient, for choose 3, and then take 1/3 to the 3rd power, and then 2/3, which would be the probability of failure, raised to the 1st power. So if we did that computation that way, we'd get the same result. So that's for binomial probability formula, just calculating a direct probability. Okay. So now we'll look at example 16, or problem 16 in the back of the book. Here we're rolling a single die 4 times, and we're interested in how many 6s we'll observe out of those 4 rolls. And for problem 16, we want to calculate the probability of having at least 2 6s. So this is at least, when at least means greater than. So recall that to actually calculate this probability directly, we would calculate the probability of 2 plus the probability of 3 plus 4 plus 5 plus 6. So that's a lot of probabilities to compute. A better way to do it is to use the complement rule. which says that the probability of at least 2 is the same as 1 minus the probability of at most 1. And so here that would just be equal to 1 minus p of 0 minus p of 1. So this is a simpler computation to compute. Now the good news is that if we were doing it by, so if we were doing this by hand, then we definitely want to take the second route. This would be the better route. But because we have a calculator, it really doesn't matter, except that the calculator can only do these less than or equal to probabilities. So there is no way to directly do this greater than or equal to probability in the calculator. So actually, even doing it with the calculator, it's best to take the second route as opposed to the first route. So, excuse this mess here. To get this piece, the probability that x is less than or equal to 1, we're going to use the binom CDF function. And here this has the same inputs as before, but it's NPK, but now the NP and K have all changed. So the N is 6, there's 6 rolls. The probability of success is 1/6 because all outcomes are equally likely with a 6-sided die. And the number of successes is up to 1. So we put 1 here. So the CDF function actually counts. It computes P of 0 plus P of 1, but we only put in 1 because we tell it what to count up to. Okay. So let me try to get this all on the screen. So that's, oops. This is the computation we're doing. Again, to pull up the binom CDF function, we hit second, we hit vars, we then scroll down till we get to the binom CDF. And so again, this has the same inputs. N is 6, P, the probability of success, is 1/6, and K is 1. So we get 0.736775549. So that's the probability of at most 1. Okay, so once you have this probability, you can now calculate the probability of at least 2 by taking 1 minus that result. So the probability of at least 2 is equal to 1 minus this long number. And that is 0.263222451. Okay, so when you have these at least probabilities, it's best to take the complement approach, because this, for one, this is a smaller computation, P0, P1, as opposed to P2, P3, P4, P5, P6, but also because the calculator can only do these at most probabilities here with the less than or equal to. So that one we can use the calculator for, and then we can put it together to get this result. Okay. Okay, so Last example from section 7.3. Here, this is number 35. Here we're tossing a coin 100 times, and we're told that the probability of getting at most 49 heads is 0.4602. We're also told that the probability of getting exactly 50 heads is 0.0796. Now we're asked to find what's the probability of getting more than 50 heads, more than. Okay. So again, this is a good place to use a complement, because this would be the probability, 1 minus probability of getting at most 50. Now, at most 50, we can think of as at most 49 plus 50. So notice how these are equivalent. Up to 49, and then we add the 50 there, and that's the same as up to 50. So these are the same thing. And what's great about that is that they've given us those numbers in the prompt. So now we just have to do 0.04602 plus 0.0796. So 1 minus parentheses 0.4602 plus 0.0796. And that gives us 0.4602. Interesting. Notice that these are the same numbers. Why might that be? Because when we're dealing with a coin toss, the probability of success and the probability of failure are both the same. They're both 50%. So that means that if we look at the histogram for this particular probability distribution, it'll be a symmetric histogram. So it'll look sort of like this. And we were told that the probability of at most 49, which is almost half, if this is 50, then 49 is 1 shy of 50. We're told that that probability is 0.4602. So since this whole thing is symmetric, if we take 50 out, then we get the what's left is the probability of greater than 50, which is exactly this area. And you can see that they should be equivalent. So that makes good physical sense. All right. Part B of this problem says, what's the probability of at most 50? Well, we sort of already went over how to compute that. So probability of at most 50 is the probability of x is less than or equal to 50, which we know is the probability of x is less than or equal to 49 plus the probability of 50. And these, again, are numbers that we were given. So we add those up. And we get 0.5398. So that's a few examples using the binomial probability distribution and different sorts of computations we could do. Okay, so now we're going to move on to section 7.4. Here, remember, we were talking about the mean or average or the expected value. We learned that these were all equivalent computations, right? So in this problem, problem 6, we're given a probability distribution and asked to find the expected value. So remember how this works. If you're given a probability distribution and you want the expected value, then all you have to do is take the value and multiply it by the probability in each case, and then add up all those results. So I would take -1 times 0.1, and then add -0.5 times 0.4, then add 0 times 0.25, then add 0.5 times 0.2, then finally add 1 times 0.05. So all we did is take each value and multiply it by its probability, and then add all of those up. And that will give us the expected value. So let's do it. So -1 times 0.1 minus 0.5 times 0.4 plus 0 times 0.25 plus 0.5 times 0.2 plus 1 times 0.05. Sorry about that. And if I did it right, then we should have -0.15. Okay, so this is a good example because we see that getting a negative expected value is not a problem. Expected value ultimately is an average, and it depends upon the values that are possible in that given context. So if negatives are possible, then so is a negative average. Y'all just bear with me for a second. I need to get my chargers before my phone dies. All right. Okay. So that's how you calculate expected value. Getting a negative result is not a problem whatsoever. Okay. Next problem is problem 15. Here they say you place a $1 bet on 1 out of 38 numbers in a game of roulette. You'll win $35 plus the return of your bet if the ball lands on the number that you choose. Otherwise, you'll lose the bet. So we want to write down the probability distribution for the earnings that you could make. So there's a lot of ways that we could write this down. The random variable will be simply x equals, if you want to think about how to define the random variable is x takes on the value of whatever the ball lands on in the game of roulette. So it could be 1 out of 38 numbers. And then we'll be asked to compute the probability. But really, it's not, sorry, I misspoke. So x isn't the number that you get when you play the game of roulette. X is the earnings that how much money you make, right? So let's just do this simply. There's 1 out of 38 numbers that's correct. That means there's 37 numbers that are not, that you'll lose on. So let's start, So let's start with what happens when you lose. So if you lose, then your earnings will be -1 because you've made no money. You lost money. You placed a bet and you didn't win. The probability of losing is 37 out of 38. because there are 37 numbers that you can lose. If you win, then you get $35 plus the return of your bet. So that's actually an earning of $36. Because you've already, what is it actually? Hold on. Sorry. Is it, you get the return. So you actually end up earning, sorry, only $35 because you are returned the dollar, but the dollar was already a loss. So you put the dollar down, and at that point you're -1. Then you earn 35 plus that dollar back. So you end up with a net of 35. So $35 would be your winnings, and the probability of getting 35 of winning is 1 out of 38. So this is the possible earnings versus the probability of getting of either losing or winning. So you can actually see this is a binomial probability distribution, but we're not worried about that in this case. Okay, so once we write down the distribution, we can then calculate the expected value. So the expected value of X will simply be the value times the probability and add all those up. So -1 times 37 out of 38 plus 35 times 1 out of 38. Aha. So isn't this interesting? So I'll just round this result. So the expected value is -0.05263. The expected value in a game of roulette is negative. What does that mean? That means that you're more likely to lose, yes, but what it means is that the house is more likely to win, and that on average, everyone loses about 5 cents per bet. And that means that the house on average wins 5 cents per bet on average. So in other words, the casino is making money. Okay. And so we're going to look at one last example here. Here, Jose wants to earn a 90% overall grade in a class. Currently, Jose's grades are 83%, 92%, and 89%. What grade does Jose need to average on the next 3 assessments to earn a 90%? All right. So let's do this. So we're calculating an average. We know 3 of the values already. We're going to add 3 more values to these known values. And when we average it all out, we should get 90. So I put down 0.83 plus 0.92 plus 0.889 from 3 averages already. And then I'm going to add 3 more values, but I don't know what those values are. So it's going to be 3 times X, because there's 3 grades, 3 new grades. Overall, there's 1, 2, 3, 4, 5, 6 assessments. When we compute this average, we want to get 0.90. So we just need to solve for X. So start off by adding up these numbers, 0.83 plus 0.92 plus 0.89, and that gets you 2.64. So 2.64 plus 3x over 6 equals 0.90. All right. Now we will bring up the 6. And that gives us 2.64 plus 3x equals 6 times 90. Sorry, 6 times 0.9, which is 5.4. And now we're just solving for x. So we subtract the 2.64 over. And we got 5.4 minus 2.64 here. And that gives us 2.76. Finally, divide by 3. And we get 2.76 divided by 3, which is 0.92. So this implies that on the next 3 assessments, Jose needs to make a 92% on each of those 3 assessments in order for his overall average to be 90% in the class. Okay, so that's the end of the problem session for 7374. I will be putting up another homework assignment. Again, there's no more due dates for homework assignments, and you'll have to help me solve this and view an example. Features enabled. Please don't abuse them and overuse them because they're only going to make you weaker students. So they're only there really to bail you out when you're really stuck. I do not recommend using them all the time, but I can't be there holding your hand the whole time. So do what you want, I suppose. All right. Y'all have a nice weekend.